Okay, now we can move to the next talk, which is Edward Hyer on the FLAMBE data set. And yeah, thank you. You can share your screen, Edward, whenever you're ready.
Okay. Is that showing properly?
Yes, looks good.
All right, I'm Ed Hyer from the Naval Research Lab, and this talk is going to mention FLAMBE and then discuss a lot of sort of scientific results that are underneath and in front of a lot of what we're discussing here in terms of estimating emissions from satellite. So I'm going to talk about FLAMBE and the specific problem that was designed to solve, a little bit about the practical considerations, but mostly this talk is going to be about the signal of active fires in the satellite fire observations and what that signal is composed of, and what that means in terms of estimating emissions. So the Navy forecasts global aerosol transport for tactical operations and decision making. So when are events like this going to occur? How long will they last? What are the areas they will affect? So this is a very practical aspect of this. This is different from a lot of the air quality applications that are primarily concerned solely with the surface and the breathable air. This is concerned with the air in the entire atmospheric column, and more concerned with the optical impacts than with the physical consequences of the particulates. However, I consider this still to be air quality science because visibility is air quality, and also because a lot of the things that make this a difficult problem are very much in common between the problems of air quality and problems of visibility. So we run a global model, running global forecasts 4 times a day at 1/3 degree spatial resolution. We're in the process of transitioning a new system with 1/4 degree resolution. This is a global system, runs 35 vertical levels from the surface to 100 hectopascals. So this is a coarse resolution global forecast, but it runs 24/7, 365 in real time. So in terms of what's needed to make a smoke source for the system, it's a component in a numerical weather prediction system. So it must be fully automated, it has to operate in near real time. But late data is not nearly as useful. The data utility drops off dramatically from later. The system is also supported by aerosol data simulation. So while we capture the fire information, we use that to estimate the smoke source, we do also have a simulation of the satellite aerosol depth that allows us to get some downwind constraint of the magnitude of plumes. That means that there's a greater emphasis on the timing and location of fires relative to the magnitude of smoke. Now, we'd still like to get the magnitude of smoke as accurate as we can. Also want to point out that our aerosol data simulation is only 2D, so it does not help us with the smoke height. So that has to come from the inventory and the model prior and so forth, because the aerosol data simulation doesn't actually give us information to constrain that. So FLAMBE in one slide, I will spend a little bit of time on this slide, but it is just the one slide. FLAMBE is the fire locating and monitoring of burning emissions. It's 24/7, 365 in Navy operations since 2007. There's a publication by Jeff Reed in 2009 that describes the system. And as it exists today, it is largely as described in the Reed et al., except that the system that's currently operational is now entirely MODIS-based. It was designed and built to use both GOES and MODIS fire detections. But in the transition from GOES to GOES-R, there was a gap in the GOES fire detections. We switched to MODIS only, and we've never switched back. It uses fuel loading and consumption based on field measurements mapped to satellite-based land cover, applies a climatological diurnal cycle. The emissions factors are traceable to field measurements using the methods that are very similar to what Johannes described in the Apavi and Andrea papers. And finally, the emissions are scaled to fire detections. FLAMBE does not use FRP, which is ironic. I'm going to spend most of the rest of this talk talking about FRP. The at-satellite resolution part is one thing that FLAMBE is relatively unique, one aspect. At this point, FLAMBE is not unique in many aspects, besides being somewhat out of date. But at satellite resolution, what that means is that the estimated emissions calculated are mapped back to the locations where satellites detected fires. And what that allows us to do is that allows us to feed these emissions to a global scale or regional scale model at a widely different resolution, and not have to do lots of fancy renormalization to get smoke closure, which is important for the system because it does support both the global aerosol prediction system as well as regional predictions of aerosol. So fire-rated power, just backing up a little bit to consider, okay, what are we trying to do with observing fire-rated power from space? So we have combustion, exothermic reaction, 14.2 megajoules per kilogram of cellulose. Cellulose is obviously not the same thing as biomass. This is a number that's readily available in literature, so we'll use it. How much energy might make it to space? There's a nice study by Bob Cremens that breaks down where the energy from combustion actually goes, how much goes to the ground, how much goes to convection, and how much is radiated and how much is radiated upward. So that's about 17% by that estimate. So if we take those, napkin numbers, we have a nominal FRP from space of about 2.83 megajoules per kilogram. We compare that to Martin Mooster's laboratory numbers of 2 megawatts per kilogram per second for biofuel consumption, and we see that we're actually in the right order of magnitude, surprisingly enough. So it is at least possible that the enormous variability in all of the factors that govern this fraction of combustion energy that escapes to space may average out. So in other words, the average net value of our satellite-based energy might actually translate fairly effectively to this combustion energy. So there's hope, based on this simple calculation. And it's good that there's hope because that's how everyone uses this product. They use this FRP as if it is a direct translation to the combustion energy release. So that term, of course, will vary with field type. So that's one major uncertainty. There's many major uncertainties throughout the system. But I mostly wanted to make the point that FRP is used as something that scales to combustion energy release. And there is reason to believe that that's not an unreasonable model, but there are also very significant components of that uncertainty that are very rarely treated in application. So active fire detection, this is an ancient slide, and the picture is different when you look at a 375 meter mirrors pixel, as I'll show. But qualitatively, we're still in this place, and we will remain foreseeably in this place. That most fires does not necessarily mean most fire activity, but most fires are missed. So the great example, majority by number, by instances of detection, are fires that are too small to see from space. In some ecosystems over some periods, the total emissions are dominated by the largest fires, but the largest fires is a scale dependent term. So that really depends on what scale you're looking at. And many fire regimes do have strong spatial and temporal covariance, so the fire activity can be scaled even with detection. So if the covariance is strong enough, then it doesn't matter that you only see the very largest fires because you can accurately scale to the total activity from that. The other thing is that the spatial resolution, we have to keep in mind that, we're all impressed with the advancing march of spatial resolution that we get from weather satellites. The weather satellites, of course, we use them because they provide the coverage and the temporal repeat that we need for this application. But the big box here is the MODIS pixel from middle wind swath. And the red area is the fire front observed from aircraft. This is the AMS wildfire at the Nasi ground at about 20 meter resolution. So this fire front is 2% of the MODIS pixel, but this is a huge, huge fire. So So overwhelmingly, when we consider looking at the signal, we have to consider that all of the satellite pixels that we're looking at, overwhelmingly, the area over which the pixel energy is integrated is not burning. So here's just a picture of that fire. That fire is famous because it threatened JPL, so that's why this picture was taken. But this is an extremely large fire, taking up 2% of the Merck's pixel. So clearly, the ability to constrain the background temperature, the non-burning temperature, is going to be very important in terms of quantitative information from the FRP group. So if we have FRP, do we now know what's burning, or do we need to know what's burning? So that the concept of fire power, as it was originally conceived, is like, hey, this is something that maps directly onto the rate of fuel consumption. We can skip all of this land cover mapping. We can skip so many steps in terms of characterizing fuels because we have a piece of information that maps directly onto energy consumption from the burning. But as soon as that was said, it was clear that it wasn't going to really work that way. So smoke on the y-axis, FRP on the x-axis. So this is from a 2005 paper. This insight is from a more recent paper, 2019. And the point is that when you look at different fire regimes, you have radically different relationships between the observed smoke and the fire of energy. Now, some of that is the complexities associated with aerosol, as discussed by Vito. Carbon monoxide is a much cleaner way to do this type of relation, but it's been done several times, and we've already seen a few other examples in previous talks showing this variability. So mostly what this is, in my estimation, is this is a sampling bias, fire energy, fire duration versus sampling, and the distribution of the fire size. So if these sampling factors could be directly accounted for, then maybe we actually could use the fire energy without geographic data. So that's an hypothesis. If we understood the sampling bias, could we use the fire energy? So some proxy for the fire regime properties is needed to extrapolate the satellite. So how can we separate sampling versus detectability? So this was covered really nicely in Johannes' slide. I think the several of the groups presenting here have methods for this that are adequate. And but I still have to show this animation if I like it. But we want to process every pixel. We want to get the variation between sensors. We want to get the variation within sensors, especially for the polar orbiters. That angular variation is very important. Sensitivity to cloud is a significant factor that we have to consider, that there are a lot of detection circumstances where the clouds are not binary on or off in terms of their interaction with the fire detection. So this does mean that this is a fairly intensive, data-intensive application, process every pixel of the satellites to do this. NRL uses the geolocated information processing system to do this type of bulk processing for analysis. So let's look at the shape of the FRP distribution within a single fire regime. So this is an analysis based on South America. So South America observed by MODIS looking straight down is the blue curves. MODIS at the edge of the scan is the red curves. And then South America, the little piece of South America that is observed by the Meteosat instrument. So that's kind of a worst case because you're over on the very edge of the Meteosat disk. But there are still a lot of reported fires from Meteosat using the WFL processing. And so it's a comparison, and the take-home point here is that 50% of the firing energy that MODIS sees looking straight down, 53% of that energy is from fires that are below the 1% detection limit of Meteosat 9. And 31% of that energy that you see when you look straight down from MODIS is below the 1% detection limit of what MODIS can see at the edge. So there are radical differences in the distribution of detected FRPs based on this angular variation, which is a function which is driven by the pixel size, driven by the fraction of the pixel that is burning. So there is no reference standard for this distribution, and I'll go back to this several times, that we don't know what the low end of this FRP curve really looks like, because all we see when we look at this is the artifacts of the limited detection of our sensors. So without a reference, our extrapolations can only be as good as our best available sensor at nadir. Now, that best available sensor at nadir is improving, but I'll show you what that means in terms of our ability to extrapolate and therefore normalize between sensors, and also try and get to true values of total emissions. So this is looking at Southern Africa fires. You saw some curves like this in Johannes' talk. So this is fire rate with power on the x-axis and fire rate with power density on the y-axis and the log scale. And what's been done here is to take the BBURNED daytime and nighttime, separate those, and separate the swath into the 3 sampling modes of the BBURNED instrument, and then do a similar division of MODIS, although MODIS has the same sampling mode across the scan. And what you see is that these curves all adopt the same shape. This shape seems to reflect the behavior of this type of detection in this fire regime of Southern Africa. And so looking at the commonality of the shape, what we did was we fitted these to a model with the parameters of being the lowest detected FRP, the shape of the FRP distribution, and what I'm calling the well-observed range. I call it the well-observed range because it's the range where all of the sensors actually see much the same thing, as long as the FRPs are high enough for all the sensors to see them. And then the most probable FRP, which is the peak of this curve. And so the fire rate of power representing the peak of this curve represents the transition from the well-observed range, where the omission errors are near 0, into FRP below this, where the detection is probabilistic. So, I built this system. I take each of these curves. I have 5 parameters that describe them. I use those parameters to recompute the FRP density, and I get within 20%. So I have a reasonably good model here for describing the FRP density of a sensor observing a specific fire regime, empirically. So okay. What about the laboratory? So there's a paper by Kumar et al. That looks at FRP from the Ruhr Fire Lab, and this is a very similar graph here. This is FRP flux in log scale, and this is probability, also in log scale, for a series of laboratory fires. And they calculated the linear fit, and that matches the fit being used here in this well-observed portion of the region. Okay, so when this linear fit is when we compare our satellite-based FRP distributions to the fire-rated flux, FRP flux distributions from these laboratory experiments, what we see is that they have a fairly similar pattern of decay, but the laboratory distributions decline more slowly than 1 over FRP, while the satellite actually declines faster than 1 over FRP. So in the satellite, we have relatively fewer high FRP values compared to what we see in the laboratory. And Kumar also found this in satellite FRP. So I don't have an explanation for that precisely, but I think it's important. But more important is to consider the low end. Okay, what about the low end? So looking at the low FRP values from these laboratory experiments. So these are laboratory burns. The signal to noise is vastly better than anything you could get with a space-based observation. And what happens at the low end of fire radiated power? So our expectation is that the low limit of fire radiated power should be the energy required to heat and dry the adjacent fuels. So there's a sustainment energy consumption, and anything below that should occur only in dying fires. So the laboratory FRP probabilities fall below the lowest FRP values. These points fall below the trend. And what that means, these points falling below the trend, is that we are sampling some of the FRPs below the sustainment threshold. So that's really good. That means that we're actually getting to the part of the curve where FRPs become uncommon because they do not produce enough energy to sustain the fuel consumption. So in this example, 20 watts per meter squared is the bottom FRP, is the lowest FRP recorded. We compare that to satellite by this calculation, very roughly, and that gives us an FRP of 1,680 watts, not megawatts, just watts. That's pretty low. So compare that to the VIIRS nighttime 375 meter detection, which is the most effective detection we have, the most sensitive detection we have, has a limit of about 1.14 megawatts. That's the limit here. That's the non-probabilistic. So that's the beginning of a well-observed. So fires above 1.14 megawatts are well-observed by VIIRS at night, whereas fires smaller than that are only probabilistic. Okay, so the laboratory results indicate the power law holds down to at least 100 watts per meter squared. That power, it corresponds to about 1 to 3% of the VIIRS 375 meter detection limit. So in terms of this curve, in terms of this distribution of FRPs, what these lab results are telling us is that this linear regime, this log linear regime, extends down 2 orders of magnitude further than what our satellites are actually able to capture. So what does that mean in terms of the total FRP? So, we have this model of the curve. We can estimate bulk FRP per area. We can relate the parameters of that curve to the pixel footprint size and the FRP detection limit. So if we put in detection limits consistent with 100 watts per meter squared, we get 5 or 10 times more FRP per area than current satellite product. So that's an example of a very crude calculation of trying to use the laboratory data to estimate how much fire we're missing with the current satellite products. So I want to put in a pitch for aircraft data and other high resolution data, because we really need that to make the bridge between the laboratory and the actual open biomass burning regimes we're observing. So very provisional summary. The translation of fire radiated power to fire radiated energy will vary by fire regime, and it will vary even if you have a 10-minute FRP. These variabilities of sampling are not just the limitations of sampling from polar orbiters. The geostationaries will also have corrections to make for properties of the fire regime. Going from fire radiated energy to emissions, the strongest sensitivity is to that limit of fire radiated power detection. That limit of fire radiated power detection is, in my analysis, pretty clearly the #1 factor in how emissions are going to be scaled. Both of these types of scaling are key to effectively combining FRP observations And if I have a few minutes left in my half hour, I think I have 3. So I just wanted to glance on some other issues that this audience might have some feedback on that I think are really relevant to the problem. So here's the acknowledgements. I want to thank the NRL Atmospheric Prediction and Effects Section and the Modus and various fire product teams and the WFALA Fire in Wisconsin for this work. But here's some bonus content. Canopy obscuration. I'd love to hear from this audience what people believe is or what people intend to implement. The Roberts et al. Publication that's used in this figure estimates 15% FRP obscuration for severe observation for Africa, but this effect is going to be much bigger for polar orbiters than it is for geo. And of course, there are fire regimes where the burning is literally at the surface. So the Matthews et al. Paper discusses some of that. So this is potentially, I think we're reaching a point where potentially this is a meaningful limitation in the accuracy of our emissions is this canopy obscuration issue. Bispectral fire regimes, we haven't heard anything about this in the talk so far, but obviously a method that's been used in many applications is to use 2 infrared wavelengths to retrieve 2 properties, generally formulated with size and temperature. There's a very rigorous analysis of this by Rosilio and Wilfred Schroeder. And the bad news is that getting fire fraction within a factor of 2 requires +4 sigma above the background. That only occurs in 7% of most fires, but it's going to occur in a larger percent as we, or in a larger number of fires as we get finer resolution detections. The good news is we know exactly which 7% those are, and they're the ones we actually care the most about. So I would say that we should not entirely give up on this prospect of extracting information from the spectral content of satellite signal. It is not hopeless. But it cannot be done for all fires because the signal is just too small. I think everybody's seen this, but fire location within the satellite pixel is an irreducible uncertainty when you're using active fires that you can describe it statistically, but you have to be aware that there's a fundamental per pixel uncertainty associated with this that you just can't get around. So that means that when we talk about limited detection, it's a range from the absolute actual minimum, which is the best case by luck, the fire happens to be in the peak of the footprint, to about 2.5 times that. Flaming and smoldering, there's been some discussion of that, and we point out that there's some papers by Jim Wong and his group, recently one in 2023, using the spectral information from the visible plus the infrared to characterize combustion phase at night. I think that's very exciting stuff, and I think that, you know, this method has limited application because it only works at night. But I still think that we can prove that there's compositional information in there, and that would be a very exciting advance. And then we just have to figure out how to do it during the daytime when fires are burning. And lastly, what is the emitter? So just, you know, underneath all of this is the thermal detection. Underneath every active fire-based application is the thermal detection. And that translation from the satellite radiance to temperature and emission, radiant emission, goes through this emissivity. So the laboratory and field evidence suggests that black body and gray body essentially works at 4 micron and 11 micron. But what about shorter wavelengths? We're seeing a lot of applications to use shorter wavelengths. And we need to know what is actually the effective emitter and what is the emissivity, because that is foundational. That is underneath all of the remote sensing that becomes fire-rated power. So that's all I have. I'm going to stop sharing and see if there's any questions.
Thanks so much, Ed. It was great to get all that extra information about the satellite retrievals and all the concerns. I'm a little overwhelmed with all the uncertainties. There are some questions in the chat. Did you want to read them, or do you want me to read them out, or I can even call on the people?
So Nancy wants to hear about the canopy obscuration. Is the percent of energy detected a theoretical amount given no canopy? Okay, yeah. So I had a slide about that at the end, I guess. I have not done any of my own work on canopy obscuration. So that slide was purely just compiled from literature. I think it's a problem that I have ignored because we have factors of 5 differences in some of the important factors. But as we narrow down those factors, I believe that canopy obscuration starts to come into the realm where it's a meaningful pole of uncertainty. Like it's no longer just completely outside of the errors that matter. It's now one of the errors that matter because we've gotten better at some of the other parts of the problem. Shoba, how do we reconcile that we only have to scale up smoke particulates and trace gases like CO? I think there's going to be a lot of discussion about that throughout this meeting. So that's a good topic sort of for the whole crowd. All right, so that's all the questions that I see in the chat. So if there are any more questions.
Yeah, we still have 8 more minutes, so people feel free.
Maybe people might get it very quickly. Happy to answer any questions. In Canada, a majority of the area burned with like ground fires. Yes, Carrie Anderson, I would defer to you on that, but I do agree. I feel like the question that I asked Amber Soya during her PhD is still not answered to my satisfaction. Can we see surface-only burns in Siberia from space? I don't feel comfortable that I can say yes or no, we can or cannot see those. If someone feels confident in their answer, I would love to hear it. Nova wants to know how I'm planning to use this research in practical applications. I wish I had a more of a plan to lay out, but what I think will come out of a workshop like this, and I'd like us to discuss it more the next couple of days, is that this is a problem of definable parts. And we need to look for avenues and ways that we can take the best approaches for each of these parts from the different groups and make synergistic products. Because everyone who builds emissions estimation from satellite has to solve the same set of problems, and they've all solved them in slightly different ways. So what we have right now is this ensemble, but I would like to see explicit ensemble-based studies of science, but I would also really like to see looking for synergistic approaches where the best takes on each little sub-problem can be assembled together to make the best overall estimation.
Okay, there's a hand up. Jacqueline, do you want to unmute and ask?
Sure. Can you hear me? Okay. Hi, Ed. Thanks for that. I'm going to try to oh, okay. You can see me now. It was a great talk, and I'm from NASA FireSense. I'm the project on NASA FireSense, and it would be, it'd be great to connect with you about sort of these synergistic opportunities. And so for the fall of 2023, we had an airborne campaign where we were flying the master sensor as well as other thermal sensors and Avarice 3 over some prescribed and wildland fires, and thinking about the coordination between the airborne sensors, ground measurements, and then the Earth orbit sensors would be, it's something that we're thinking about. And so the questions that you've brought up are, potentially we could have some of that synergy as part of that campaign or future campaigns. And we did not do any emissions sampling as part of the 2023 campaign, but it's definitely on our agenda for future campaigns.
Yeah, I think that the existing aircraft instruments are underutilized. They are also imperfect, but even imperfect as they are not. We have not gotten everything out of them that we can in terms of the science. So I'm glad to see that's still on the table, and NASA is supporting more field collection.
Well, and so we have a solicitation out right now for interested parties to apply to be considered for the implementation team for FireSense, where you would be able to, contribute your thoughts on the science and those connections. And I can put the link into the chat, and I'd open that up to, everyone on the call if you haven't seen it already. Thank you. It was a great talk.
So Cindy, it seems to have crashed. She will be back, I'm sure. But do we have any other questions for Ed? Okay, so yep, Cindy's not quite available right now, but we have another few minutes if anybody has any questions. Ed, I have a lot of ideas of things to talk to you about. One of the things that Christine Wiedenmeyer and I just exchanged a little bit about, and we've talked about already, is this idea of how to improve what is mapped for fuels and fuel loading in a global sense. So I'd love to dig in a little bit more with you on how you do that aspect of it. You had a bullet point, I think, on that on your slide. Is it fancy, or do you just do something kind of easy?
Yeah, so this is definitely let's talk about how to do it, which is because how I do it is not something I'd recommend to anyone. I think that the ways that it's being done for Finn seem to capture and reflect the strengths and limitations of the land cover data sets. But as Christine showed, the land cover data sets remain this huge wheel, and FRP-based approaches, they actually can mitigate that to some extent, but they can't eliminate it. So that issue of what are the land cover products that actually capture what we're trying to get at in terms of fire regime differences, that's a legitimate one, and I certainly don't have a practical answer. And I think it's a good scientific question to discuss.
Yes, I agree. And one thing that Christine's Finn does is work with at least temperate North America, CONUS refined kind of best fuel loading capabilities there, and then elsewhere other things, but that allows us to use at least some type of landscape to understand the uncertainties and the drawbacks to the global choices that are made. So we may be able to do a little bit of testing within North America using that more refined information on fuels. There is one other comment from Fang Jun in here. According to Wooster's early research, mid-wave-based FRP works best for fire temperature between around 400 and 1200 K. For small, cooler, more intense fires, the reliability seems like we need more research, which I agree. And since Jackie Schumann just mentioned FireSense, there is some effort to collect broad hyperspectral midwave data on fires. In fact, they flew some of those fires at night or without the sun, so that was helpful for some of that type of understanding of what we get for fire energy in places that are outside of the or inside the reflected solar reflectance area. So nighttime flights, that's one thing we can do, and more airborne stuff. So we're getting very close to, I think we have 1 more minute. Cindy, are you back? Okay, then I think what I'll do is, okay, is Arlindo on? That's a question too, because Arlindo is double dutying. He's off at another conference and then coming on. Yes.
Oh. He needs a Zoom link. He just sent an email.
Yeah, I just sent him mine.
Okay.
Okay, good. Yeah, he just sent an email to me. So good. I think, Christine, that's helpful. See if he can come on. And actually, sorry, technical difficulties. We do have his slides if we have trouble with him with that part, but I'd like to have him come on as a presenter, obviously. So we'll take a short little break, unless, Ed, you want to pontificate on anything else, as you're very good at doing when we need to fill time.
I think pontification while we're waiting for Linda to get connected. I'll just type up a reply to Van Good's comment. But yeah, I think this is going to be a very, very good discussion tomorrow based on the talks that we've had so far this morning. I'm very glad to see the group that's been assembled here.